Let's talk a little bit about quadratics, because so far the only type of equations we've really talked about were linear equations, right? Y equals mx plus b. But there are other types of equations, right? Not all graphs are just straight lines. So a quadratic is something that looks like this, y equals x squared. And that's the most basic version of a quadratic you can have, right? And if you make a table of values for that, x and y, you can plug in some points for x and you can calculate some points for y based on that, right? So you plug in -2, -1, 0, 1, 2, and you plug those into the equation, right? -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4. You can see that the pattern in both directions kind of repeats itself, right? This is going to be a symmetrical shape. And so if we go to graph this, x and y, say, okay, 0, 0 is a point, 1, 1 is a point, -1, 1 is a point, and you go to 2, you're up here at 4. If you go to -2, you're also up here at 4. That continues, right, in both directions. And what you get is this cool little horseshoe shape that goes like that. That's perfectly symmetrical. Now, one thing that I'll talk about just briefly is you might hear your teachers talking about first difference, second difference, third difference, that kind of thing. All that's referring to is a way to figure out the type of equation you have based on data that you see in a table of values. For example, what I'll do here is I'll make another column, and I'm going to subtract these y values from each other. So I'll show you what I mean. If you do 4 minus 1, you're going to get 3. If you do 1 minus 0, you're going to get 1. If you do 0 minus 1, you get -1. If you do 1 minus 4, you get -3. These are the numbers that we would refer to as the first difference. If these numbers were all the same, it would mean that we have a linear equation, or a straight line, but they're not the same, so we don't have that. And so what you would do is subtract them again. You'd say, what's 3 minus 1? Oh, 2. What's 1 minus -1? That's like saying 1 plus 1, which is 2. What's -1 minus -3? That's also 2. These are the second difference numbers. And because these are all the same, what that means is that we have a second degree equation, or in other words, a quadratic, right? Y equals x squared. It's referring to the exponent on that x. If you think back to y equals mx plus b, just a linear equation, the exponent on your x, there is no exponent, it's just a 1, right? So we don't have to write it. And for that reason, you would have these first difference numbers all be the same. And so there are higher exponent equations that you're going to see next year and the year after that. And you would say, oh, you can look at the third difference and the fourth difference, and then you would start to see the numbers be the same. But for now, just know that's all this is referring to when you hear the phrase first difference or second difference, okay? So this here is your y equals x squared. So this is just something that's, good to know, keep in the back of your mind, but we're not going to work with it a ton, maybe once in a while. So this is y equals x squared. Now that's, like I said, the most basic quadratic, but they can get a little bit more complicated, right? Like I could say y equals x squared plus 1. Just put a plus 1 on the end there. Now what's that going to do? Well, let's say you make your table of values, just so we can investigate this, and you have the same points, -2, -1, 0, 1, 2, and you plug them in, right? -2 squared is 4, but 4 plus 1 is 5, okay? -1 squared is 1, plus 1 is 2. 0 squared is 0, plus 1 is 1. 1 squared is 1, plus 1 is 2. 2 squared is 4, plus 1 is 5. So you still have this kind of symmetrical pattern where if you go this way and this way, you get the same numbers repeated. But when we graph this, it's going to look a little bit different than the original one we had, because at 0, you're already up here at a height of 1. At 1, you're up here at a height of 2. And same with when you're at -1, you're at a height of 2. And when you're at 2, you're up here at a height of 5. And when you're at -2, you're also up here at a height of 5, kind of going off my graph. So you get that same sort of smooth horseshoe shape if you're able to draw it prettier than I'm doing. You get that nice horseshoe shape like this. The only difference between this and the previous one, if you notice, is that this one, the origin was at 0, 0. And then this one looks to have been moved up by a unit or shifted up, right? It used to look like this, but it looks like all the points have moved up by 1 unit. Can you envision that? Hopefully you can. So when you see a +1 on the end of your quadratic equation, what that means is that the whole shape has, you could say, translated or been translated up 1 unit, or you could call that a shift if you wish. So if I had, for example, we'll just do this quickly, y equals x squared minus 3, you can probably imagine what that's going to look like. The whole thing goes down -3, so the vertex would be down here at -3. And it's the same shape. It goes up like this. So that's just a sketch, right? It's the exact same shape as this, except it goes down 3 instead of up 1. So that would be a translation down 3 units, just as an example. Let's look at a different way we can complicate these equations. Because before, I had an x squared plus a number out here. Well, the number doesn't have to be on the outside. It can be on the inside. What I mean by that is it can be included in the thing being squared, kind of like this. So now this 1 is on the inside instead of on the end on the outside, right? It's being squared along with the x. So this doesn't represent a vertical shift or a translation up or down. It's going to represent something else. To figure that out, let's do our table of values to see what happens. And you can make a prediction right now as to what you think is going to happen when there's a +1 there. And we'll see if you're right. So I'm going to put the same x values, I'm going to plug them into my equation. So -2 plus 1 is -1, -1 squared is 1. Okay, interesting. What about -1? -1 plus 1 is 0, squared is 0. 0 plus 1 is 1, 1 squared is 1. 1 plus 1 is 2, 2 squared is 4. 2 plus 1 is 3, 3 squared is 9. Okay, interesting. So let's try to plot this. So we have x and y. So the first point we have here is -2, 1. So I'll put it right here. -2, that's at a height of 1. You have 0, or sorry, you have -1, 0. So you're right there. You have 0, 1. So that's at the same height as the -2 over there. At 1, you're up here at 4. And then at 2, you're way up here at 9. So if you follow the pattern the other way, if you go to -3, that'll also be at a height of 4, right? Because it's the same pattern on both sides. And it has to make this, this horseshoe shape, right? Same on both sides. So what's happened to this compared to the original function, right? The original one looks something like this. It looks like it's moved over to the left by 1 unit, right? The vertex used to be here at 0, 0 at the origin. And this is called the vertex, that point that's right down at the bottom in the middle. And it looks like it's moved over to the left by 1 unit. So you made your predictions before, and some people would predict that because it's +1, it would move to the right. But actually what's happening here is we are translating 1 unit to the left. And you could say it's a horizontal translation, 1 unit to the left, right? It means the same thing. Just indicates that we're working left to right instead of up and down, right? Then you would call it vertical. But that's all we're doing here. So if I gave you another one, like y equals x minus 4 squared. So a +1 meant 1 to the left. So -4 must mean that we're going forward to the right. And indeed it does. So over here at 4 is where your vertex would be. And you would just sketch your graph, something like that. So it's the exact same shape, but it's moved over to the right 4 instead of to the left 1. Hopefully that makes sense. Now what other types of things could I do to these equations? Right, so if we recall that our original, right, the most basic one I said was y equals x squared. And let me just graph that quickly, right? Just so we have something to compare to. So that's what that looks like. What if I have y equals 3x squared? Well, if you do a table of values, right, x and y, and you plug in the same points, -2, -1, 0, 1, 2, those are easy points to see on here, right? And you plug them into your equation, what's going to happen? Well, -2 squared is 4, so you used to get 4, but now you multiply it by 3, so you get 12. So you get a much bigger number, right? You plug in -1, -1 squared is 1, multiply it by 3, you get 3. So you used to get 1, now you get 3. Plug in 0, that's still 0, right? Because 0 squared is 0, times 3 is 0. You do 1, you'll get 3, 2, you get 12. So it's the same pattern, it's still symmetrical, right? It goes in each direction, right? It looks the same. It goes 0, 3, 12, you go the other way, 0, 3, 12. So it's still symmetrical, but these numbers are a lot bigger than they used to be. So if you graph these, you're going to end up getting a much skinnier graph than we got in the past. So while this is y equals x squared, this new skinny one is y equals 3x squared. So what that 3 on the front does is what we call a vertical stretch by a factor of 3. So I'll just say vertical stretch times 3. That means a vertical stretch by a factor of 3. So your graph, if you can imagine, has been stretched up and down, right? It's been pulled upwards. That's how they like to describe it using words, but really the important thing to note here is that if you have a 3 on the front, these points get bigger much quicker, right? So instead of 0, 1, 4, you get 0, 3, 12, right? They get a lot bigger, a lot quicker. So you get this skinnier looking graph. And likewise, you could do the opposite, right? You could say y equals 1/2 x squared. And if you made a table of values for these, instead of all the points being 3 times as big, they'd all be half as big. So you'd get a graph that's a lot shorter, something like this. So that would be y equals 1/2 x squared. And so that 1/2, what that's doing, I would refer to that as a vertical compression. So instead of a vertical stretch, I'd call it a vertical compression. And you could say by a factor of 1/2, because each point is going to be half as tall as it used to be, because whatever answer you used to get for x squared, you get that, but then in this case you multiply it by 3, and in this case you multiply it by 1/2. So these answers are all going to be half as tall. In the previous one, they're all going to be 3 times as tall. Hopefully that makes some sense. Alright, what else could we do? Because there's a few other things, right? We could maybe have something like this. So I'm going to start with y equals x squared. But what if I have y equals, instead of a number on the front, on the outside, what if I put the number on the inside, like this? So now that number is being squared, right? It's inside the function. Well, let's sketch this out, right? I'll start with my original, just to show where we're starting. Now what's going to happen here? Let's do our table of values again. Same points, -2, -1, 0, 1, 2. Plug them in. -2 times 2 is -4. -4 squared is 16. Plug in -1. -1 times 2 is -2. Squared is 4. 0 is going to give you 0. 1 is going to give you 4. 2 is going to give you 16. So these numbers are all a lot bigger than the 0, 1, 4 that we used to have, right? In just the regular function. And so this is also going to get taller and skinnier. Just like how if there was a number on the outside, on the front, it made it taller and skinnier. A big number like this on the inside is also going to have a similar effect. So this is y equals 2x squared. The thing that changes, though, is the name that we give to this transformation. And that's what these are, right? These are transformations. What we call this is a horizontal compression by a factor of 2. So in the past, when it got taller and skinnier, right, like if it had a 2 on the outside, I'd call that a vertical stretch. But if it's on the inside of the function, funnily enough, we call it a horizontal compression. So if you think of double negatives, right, a vertical stretch and a horizontal compression, they really do mean the same thing, right? They mean very, very similar things. They're having a very similar impact on our shape, right? It's getting skinnier and taller. But we call it horizontal because it's on the inside of the function, right? And it's directly impacting x. So if it's on the inside of the function, whether it's a shift left or right, like a translation, or if it's a number on the front that's being multiplied, so a horizontal stretch or compression, that's all horizontal. If it's on the outside of your function, like a number on the outside, or you're adding a number on the end, that's all vertical. We label those as being vertical transformations. Okay? And of course, you could have a number that's less than 1, like y is equal to, 1/5 x squared. So the number on the inside is less than 1, like a fifth. That's what I would call a horizontal stretch by a factor of a fifth. And so horizontal stretch by a factor of a fifth, that would make it something like this. So that's y equals 1/5 x squared. And you might hear some teachers saying like, okay, well this is actually a horizontal stretch by a factor of 5 because it stretched it out horizontally 5 times. And so you just use that number. I've seen people use kind of both ways of thinking about it. I think the safest way to make sure that you're doing it correctly and you're getting full marks is you just use the number that's there, right? So if you'd say this is a horizontal stretch by a factor of 1/5, it's probably the safest option for you, although sometimes I've seen people do it differently and I understand why. I don't completely agree with writing it like this. I might call this a horizontal stretch by a factor of 5 because it's becoming more horizontally stretched. But again, if your teachers do it this way, follow that. But again, you can see why there might be some confusion with the naming conventions and the factors, right? Let's look at something else. Let's say, and again, we're just going to start with y equals x squared, so I have something to compare to. Let's do a question where we have maybe multiple transformations. Like what if I have y equals 3 and then a half x squared? So this 3 on the front, we know what that does, right? It's a vertical stretch by a factor of 3. I know what the inside does, right? That's a horizontal stretch by a factor of a half. So the question is, if this is your original function like that, is this thing getting taller and skinnier, or is it getting shorter and wider? Because a vertical stretch makes it tall and skinny, and a horizontal stretch makes it short and wide. So if you have both of these things going on at the same time, which one's winning? Is it the 3 or is it the 1/2? Well, one thing you can do is you can expand this square into the bracket. So you could say y is equal to 3 times 1/2 squared times x squared. And what happens then? Well, you get 3 times, well, 1/2 squared is a quarter, x squared, and you can put those numbers together. You can say 3 over 4 x squared. And then we can look at this number here, 3/4, and we can say, is that bigger than 1 or less than 1? Because if it's bigger than 1, the shape is going to get skinnier and taller overall. But if it's less than 1, it's going to get shorter and wider, right? That's the pattern we've seen. Well, when you combine those two numbers together, the 3 and the 1/2, they give you a number, 3/4, that is less than 1. Therefore, your final answer here, if you're just going to do a sketch, would be shorter and wider than the original. So this is y equals 3 times a half x squared, and this is just y equals x squared. Okay? So even though it looks like, okay, well 3 is bigger than 2, so it looks like the vertical stretch is going to win and it's going to get skinnier. Because this 1/2 is on the inside and it's being squared, it's not really a half, it's actually a quarter, right? And when you expand it, you see that. And because the 4 is bigger than 3, 3 over 4 is less than 1, so it ends up being shorter than the original. So that's something to keep in mind. Now there's even more things that we can do, right? We haven't even covered everything yet. We also have this. So I'll start with y equals x squared, but what if I have y equals negative x squared? There's a negative on the front now. Well, let's graph the original. So this is y equals x squared. What happens when there's a negative on the front? Well, if you do your table of values, and I don't think I have to do this to communicate the point, but if you did your table of values, every answer you get for y is going to be the same as before, except there's a negative on the front. So all your answers will be negative, and when you plot those points, you're going to get a shape that goes like this. And so if you can imagine, it should be clear why we call it this, but this is what we would refer to as a vertical reflection. Or you might hear it referred to as a reflection in the x-axis. And the reason it's called that is because this is your x-axis, and it's reflecting over that. Right? That's a mirror image if you had a mirror on the x-axis. So you might hear it referred to as either one of these, and that's okay. Now, there's another possibility, right? So you could have y equals, and then the negatives on the inside, so it's negative x squared. Now, if you remember what I said earlier, every transformation on the outside of the function, so anything that's not being squared, that's a vertical transformation. So in this case, it's a vertical reflection, just like how before we had vertical stretches and compressions and vertical shifts or translations. But if it's on the inside of the function like this, it's horizontal, right? So this would be a horizontal reflection, or you could say it's a reflection in the y-axis. So this original shape is going to reflect in the y-axis. The thing is though, because this is already symmetrical in the y-axis, when you reflect it, this comes over here, this comes over here, you end up getting the exact same shape. You get a shape that's right on top of this shape. So it wouldn't look any different. So not only is this y equals x squared, it's also y equals negative x squared. It's the exact same thing, whereas this one on the bottom is y equals negative x squared. So for this type of equation, you're not going to see a difference when you have a horizontal reflection because it's symmetrical already. For some other equations, that might not be true, so you always have to check, but for a quadratic, it absolutely is true. Okay, let's talk about the general form now for these transformations, because I've given you a bunch of examples, but in general, what you can say is y equals a times k times x minus d squared plus c. This is the general form for a quadratic equation with all kinds of transformations, right? All at the same time. We've talked about these already, right? A represents a vertical stretch or compression, right? And if it's negative, that would mean that it has a vertical reflection. So if it's negative, there's a vertical reflection. The k value, which is that number multiplied by x on the inside, is a horizontal stretch or compression. This number, x minus d, your d value, represents a horizontal shift. Or you could call that a translation. I think we called it a translation earlier, right? And that's going to the left or to the right. And then your c value is the vertical shift or the vertical translation up and down, right? And so one key thing you want to note here is that the inside looks to be common factored, right? Or at least there's only a 1 in front of the x. There's no number in front of your x directly anyway. It's on the outside of the bracket. So for these questions, what you want to do is make sure the x is by itself. You've factored out that number if there's a number in front of it, because that will reveal to you the real d value. If you don't do that, you could be looking at a d value that's not really your d value. And we'll look at some examples of that. So with this information in mind, there's actually another concept that I might as well introduce to you now. It's not the most popular, but some teachers insist on using it. And so you might hear this. It's called the mapping rule. Or maybe not mapping rule, maybe instead you hear it called the mapping notation. And what the mapping notation says is if you have a point xy on the original equation, and then you have all these different transformations that we just talked about, a, k, d, and c, this point will map to a new point, and the new point will have the coordinate x over k plus d, a, y plus c. So an example of this you could say is if I have y equals x squared, that's my function, and my new function is y equals negative 2 1/3 x minus 2 squared plus 1, that's my new function. Then the old point, which an old point on here could be something like 2, 4, right? Like if x is 2, 2 squared is 4, that's a point on the original. Then the new point will follow this equation up here, or this notation up here. So x over k plus d, well my x value is 2, k is 1/3, that's that number there, so 2 divided by 1/3, plus d, d is 2, right? It's not negative 2, because remember this is x minus d, so the d is just the 2, so plus 2. And then over here you have a times y, so negative 2 times y is 4, plus c is 1. You can then simplify this, right? 2 divided by 1/3 is 6, 6 plus 2 is 8, and then 4 times negative 2 is negative 8, plus 1 is negative 7. So the point 2, 4 becomes the point 8, negative 7 on the new graph. Again, this isn't the most popular. Some teachers don't address it at all. Others insist that you do cover it. But if you need to know how to do it, this is exactly what they're referring to. Now, with that out of the way, let's go ahead and actually graph some equations that have a bunch of transformations. Let's say we have y equals 3 x minus 1 squared plus 2. So there's no k value here, right? There's no horizontal stretch or compression. There's only a vertical one, and that's just to keep things simple, right? Maybe the next one will do. It'll have a k value. So one thing I'll draw your attention to is the form that this is written in, right? I showed you the general form earlier, but this is actually what we refer to as vertex form. And the reason it's called vertex form is because you can actually see where the vertex is based on this equation, right? We can see that it moves up 2 and then it moves to the right 1. So based on that fact, right, based on the fact that it goes to the right 1 unit, it's a shift, and there's a shift up 2 units, we can figure out what the vertex is, right? The vertex is normally at 0, 0, but it goes up 2 and to the right 1. So your new vertex is at the point 1, 2. It's right there, you can see it, right? So it's this number, opposite sign obviously, and then this number, right? So 1, 2 is where your vertex is. That's why we call this vertex form, and you're going to hear that phrase quite a bit in the upcoming units. Now, how do I graph this, right? Well, let's say they just ask for a sketch, right? So I have my x and y axes here. So the vertex is at 1, 2, so I go 1, up to 2, boom, there's my vertex. Next question, does it go like this? Does it open up? Or does it go like this and open down? Which way does it go? Because they're both possibilities, right? Well, because this 3 on the front is positive, right? There's a positive in front of there, no negative. That implies that it opens up, right? So it's going to look something like this. And now we also know that there's a 3 here. That 3 is going to be a vertical stretch, right? And so this thing might be a lot skinnier, might be a lot wider. It's not to scale, but depending on how skinny or wide it is, this y-intercept is going to change. And so what we can do is we can figure out what that y-intercept is, and we can label it on the graph. How do we find a y-intercept? Well, you set x to 0 and solve for y, right? It's the same process you would use for linear equations. So I'm going to set x to 0 and solve for y. So y equals 3, 0 minus 1 squared plus 2. Okay, and again, this is defined the y-intercept. This is what you do. So y is equal to negative 1 squared is 1. 1 times 3 is 3. So I have 3 plus 2. That's just equal to 5. So your y-intercept here is at 5. So you would label that, and now you have an accurate sketch, right? Anyone can look at this and they can figure out exactly where everything is and exactly what this graph looks like. Okay, let's do another one. Let's say I have y equals negative 4, 2x plus 2 squared minus 6. Okay. First thing I want to do, and you might see this already, or you may have forgotten, that's okay, is you want to make sure that there's no number in front of the x. At least not directly in front of it, right? You want a bracket to separate them. So what I'm going to do is I'm going to common factor the inside. It doesn't matter if there's a common factor or not, like this number here could be 3, it doesn't matter. I just factor out the number that's in front of the x so that the x ends up by itself. So that could mean that when you factor out that number that you have a fraction here, right? That's okay. You want the x by itself. So you do 2. In this case, it works out nicely. It's x plus 1. You get a whole number. But again, you won't always. And then minus 6. Now we know that it actually moves 1 to the left, not 2. You see that plus 2, you might think, oh, it goes 2 to the left. But it's actually 1 because you have to common factor that first. Okay. So with all this information, we can find the vertex, right? Goes 1 to the left, down 6, so your vertex is going to be at the point negative 1, negative 6. Get that right from there. So if we're going to graph this, you could say negative 1, negative 6, there's your vertex. Okay? Now, does it open up like this, or does it open down like this? Which way does it go? Well, if you look at the front of the equation, we have a negative. That means there's a vertical reflection, meaning it's going to open down. So we can draw it opening down like this. And if you notice, it's going to cross the y-axis at some point. There's going to be a point here where it crosses. So we should figure that out just to label it, right? We want to label as much stuff here as we can. So to find the y-intercept, just like last time, you want to set x to 0 and solve for y. Because at that point, right, the point's 0, comma something, right? It's on the y-axis, so the x value is 0. That's why we do that. So y equals negative 4, 2, 0 plus 1 squared minus 6. Right? I set x to 0. Solve for y. 0 plus 1 is 1. 1 times 2 is 2. 2 squared is 4. So I get negative 4 times 4 minus 6. Negative 4 times 4 is negative 16. Negative 16 minus 6 is going to be negative 22. So that's negative 22. So that's your y-intercept. Okay, let's do one more. let's say I have y equals 5x plus 1 squared minus 4. So where's your vertex? Your vertex is at the point -1, -4. So -1, -4, say that's where it is. It opens up because the 5 on the front's positive. There's a positive on the front, so it's going to go like this. Right? I don't know if it crosses here or if it's crossing more so like on this side. Not really sure, but we can figure that out, right? So those are your x-intercepts. You have two x-intercepts, and you also have a y-intercept, right? So the last two examples we didn't have any x-intercepts, but this one does, right? And that's okay, we can find those. And those are also called the roots, right? You may hear those referred to as roots or zeros or x-intercepts or solutions. They all mean the same thing, okay? So let's find those x-intercepts or roots first. So how do you do that? You set y to 0. So 0 equals 5, x plus 1 squared minus 4, and then you solve for x. So bring the 4 to the other side. 4 equals 5, x plus 1 squared. Divide both sides by 5. 4/5 equals x plus 1 squared. Square root both sides. Square root of 4 over 5 is equal to x plus 1. And that's plus or minus, right? Plus or minus square root of 4 plus or minus the square root of 4 over 5. Because when you take the square root of something, you get the positive and the negative of that number. Bring the 1 to the other side. So you get plus or minus root 4/5 minus 1 is equal to x. So you get two answers, right? And the answers in this case might be a little bit messy, but we can find out approximately what they are, right? We can calculate what these numbers are. So one of the answers you get, if you use the positive square root, is going to be negative 0.106 approximately. And then the other number, if you use the negative square root of this, is going to be negative 1.894 approximately, right? It's just rounding. But this allows you to show approximately where those are. So this one here is at negative 1.89, so just to the left of negative 1, right? Almost at negative 2. And this one here, we actually drew it incorrectly, right? It's not going like that, right? It's going to be coming up like this, right? It's crossing here on the negative side still. So not like that, but like this, because we got negative 0.106. So that there is at negative 0.1, right? Very small number just to the left of 0. So that's where it's crossing. So that's why it's important to find those x-intercepts and the y-intercepts, because then you can draw your graph more accurately. If I drew it coming over this way, we would know, oh, there's a problem. They didn't do it correctly. So that's why you always got to find those intercepts. The y-intercept up here, we know it's up here now, right, instead of down here, so it should be positive. So let's solve for the y-intercept, and again, we expect to get a positive answer because we confirmed that the x-intercept was here, so the y-intercept must be up here. So y equals 5, 0 plus 1 squared minus 4. Again, you just set x to 0. 1 squared is 1 times 5 is 5 minus 4. That's equal to 1. So the y-intercept here is 1. So your graph is crossing the y-axis at the value of y equals 1. And that's all there is to it.